Hello everyone. I shall be very happy to start another module today. Today I intend to commence the discussion on module number 5 of your syllabus, known as, the topic is forced vibrations. Forced vibrations. So all our bad things, whatever we have from vibrations, are because of forced vibrations only. It is not free vibrations which cause problem. Okay. But then why, you may ask a question, why did we study free vibrations? So we should have gone directly to forced vibrations. Unfortunately, we can't do that. We need the study of free vibrations, and probably in the forced vibrations, once I start the analysis, you will also come to know why that is required. Okay. So free vibrations we studied under two cases, undamped and damped. The idea of knowing for undamped is to know what is the natural frequency of the system, so that we can avoid resonance. What is the resonance? Frequency, natural frequency, and the frequency of the forced vibrations, that is the excitation. Okay. So if both of them match each other or they coincide, then we see that resonance. Okay, why should we avoid resonance? If we run any system at resonance, then I think very soon you are not going to see the system. The system will fail, the system will collapse, the system will undergo vibrations of very large amplitude, and before really it happens, the system would have failed. So very severe case, and we must avoid resonance. That is why we studied what is the natural frequency of the system, so that I can decide what can be the excitation of this external what can be the frequency of this external excitation, so that they are far away. Okay. Then we also studied what is called as damped vibrations, damped free vibrations. So we know that all our systems are damped systems, and because of the damping, the vibrations, free vibrations, they are going to die out, or in other words, they vanish after some time. And we may not have free vibrations for certain systems, if the system is over damped or critical damped, like that. Okay, even if it is under damped, you have vibrations, that will go for a very short time, and after some time you will not have free vibrations. Okay, so now we shall move on to what is called as forced vibrations. This is the topic of the title of the topic of module number 5. You have a lot of things in this. Okay, don't worry. So do as much as possible, and we shall try to discuss it. And one good thing is, all the problems, numerical problems, apart from derivation, if there is any theory thing asked in the examination, all problems happen to be numerical. They are substitution like. The only thing is, we have a large number of formulae list. Okay, so which formula we need to pick it? You are supposed to remember and pick the right formula and substitute, you get it. The answer is going to be solved. You are going to get it very in short time. Though one full question normally it is expected to take about 20, 25 or 30 minutes, and you can solve it in much less time than that. It is substitution like thing, but we have lot of cases. We shall go on one by one, and let us move on and let us see what all things we can do. So forced vibrations. Okay, I have considered a system. I have built a system. So what is this system? It is a damped system. Okay, I have K, M and C. So K spring, M mass, C dashpot. So spring, mass, dashpot system. Okay. So now, where is the external excitation? Yes, right now I have not applied the external excitation yet. Okay. So what is the external excitation, and under that what is going to happen? That's what I am going to see. Okay. Right now, this system is in an equilibrium state. This is an equilibrium state. Okay, so let me draw the free body diagram of this. If I draw the free body diagram of this, you know that this is here, and the mass, okay, is subjected to a force K into delta ST. So delta ST is the static definition of that, and the mass is subjected to a weight, what is called mg, and therefore we know that mg is equal to K into delta ST. So delta ST, please remember, it is delta ST. So I shall have something little later, something suffix st. Okay. So I shall have it. I shall again. This is delta. I have used delta is a static deflection. When the mass is at the equilibrium state, okay, vibrations have not started yet. That time, what is the extension? What is the extension of the spring? That is what we are calling it as delta S. Okay. So now I am going to apply a force. What is this? The nature of the force? The nature of the force is not just F naught. It is F naught sin of omega t. If I apply only F naught, if sin omega t is not there, then this mass is subjected to force F naught in this direction only continuously. The mass will go on moving like this, and before it fails, till it will continue to move in this direction if sin omega t is not there. Okay, because the force is continuously in this direction. Because of the sin omega t, okay, after some time this omega t is such that the direction of the force is in the opposite direction. So because of this sin omega t, this F naught sin omega t, the force sometimes may be this way, sometimes may be this way, and that is why we have vibrations. We have vibrations because of this force, which is changing its magnitude and also direction. So in either way, and because of which makes the mass to move either this side or this side, depending upon what is the direction. So this direction I shall take it as positive. I shall take it as positive. The moment I apply this force, this mass will vibrate, will start vibrating. Okay. So at some instant of time, let me assume that the mass is here. Okay. This much displacement is quite large. Okay. Only for clarity I have just shown it. Okay. I know that this is the displacement and this mass, this is at t equal to t, this is at t equal to t, and this mass is having velocity. It is also having what is called as an acceleration. It is not stationary at this position. I have arrested through my eyes. I have made it to stop there. Please remember, the mass is not stopped there. It cannot be stopped unless you apply some force. I have not applied any external force. It is moving. At this position, I have arrested. I have taken a photograph and arrested it and showing what are the things that is happening there. Okay. So now let me draw the free body diagram of this. Why I am drawing free body diagram? Because I want to write down what is the equation of motion. So ultimately that is going to be a differential equation of motion. So what is that? M. Okay. So what are the forces? You know, mg is there. And the spring will try to pull it up. What is that? A multiplied by delta st plus x. And this dashpot is also offering a force. This dashpot was not offering any force at equilibrium state. Why? Because the dashpot will offer resistance force only if the mass is having velocity. If the mass is having zero velocity, then it will not offer any force, resistance force. So therefore, at this juncture, it is having velocity and it will oppose motion. Therefore, the mass is going down and therefore it is trying to pull it up, and that is equal to c into x dot. Okay. So now I know that in addition to this, it is also subjected to what is called as a force, external force, F naught sin of omega t. What is force vibrations, by the way? By the way, how do we define vibrations? During which the external excitation is present. If you don't have external excitation and if you still have vibrations, those vibrations are in the absence of external excitation. That is why they are called as free vibrations. So now it is not free, it is forced vibrations. Therefore, that external excitation is continuously present. Therefore, that external excitation is F naught sin of omega t. So I also know that it is having acceleration, x double dot. So many forces, 1, 2, 3, 4 forces, and the mass is not stationary, it is having acceleration. So what should I do? I apply Newton's second law. What is Newton's second law? Sum of all the forces, left hand side, sum of all the forces in the direction of acceleration is equal to mass multiplied by acceleration. Okay, let me start with this. So mg, the force, it is in the direction of the acceleration. Therefore, we shall write it as plus mg. Then f naught sine of omega t. This also is in the direction of the acceleration. Therefore, this also is plus f naught sine of omega t. Then further, k into delta st plus x, it is opposite to x double dot. Therefore, it is minus k into delta st plus x. Then I have cx dot, which is also opposite to x double dot. Therefore, I have one more force, what is called as cx dot. Any other force? Take it, all of them are taken, and sum of all this is equal to m into x double dot. Okay, it is not equal to 0. Please remember, we are not applying equilibrium condition, we are applying Newton's second law. So therefore, please simplify this. This is mg plus f naught sine of omega t minus k into delta st minus k into x minus c into x dot t is equal to mx double dot. So I have already shown that this mg and k delta st, they are one and the same. And so keeping this here, and I shall send these two terms to the other side and rewrite it. That is mx double dot plus cx dot plus k into x is equal to f naught sine of omega t. Okay. So what is the title of the topic what we are discussing? Forced vibrations subjected to what? Subjected to harmonic excitation. So this excitation is basically a force, and that also is harmonic in nature. Okay? So harmonic, subjected to harmonic excitation. The title of this module itself is forced vibration. This is the first case in that. So next may be force vibration subjected to rotating unbalance. Force vibration subjected to reciprocating unbalance. Of course, the balancing chapter we have not studied. Okay, so you come to know that balancing, if the system is not balanced, either rotating balance or reciprocating balance, you will have some unbalanced force, and that unbalanced force is also harmonic. Okay, so later on you are going to study that in different cases. This is what I can say, that this is the first case. Okay, forced vibrations type is going to be common, but only what is the excitation? The excitation is harmonic excitation, f naught sine of omega t. Okay, so this is what we got. Okay, this is mx double dot plus cx dot plus kx equal to f naught sine of omega t. So what is the purpose of study? What exactly I want to know? Okay, so I have applied such a force. This is m, this is k, c. I know k, I know m, I know c. I also know f naught sine of omega t. Okay, so now, so how the system is going to behave? What will be the amplitude of vibration? Okay, I want to know. So how the vibrations are going to be? So therefore, I need to know. So I am not going to be happy with this. I want to solve this equation. I want to solve this equation. So what all things I know? I know k, I know m, I know c, I know f naught, I know omega. That means k, m, c, m, f naught. All these things are known. These are known. Okay. In addition, when you know this, you also know some things later on. That is derivative. So you know Cc. Cc is equal to 2m into omega n. You know omega n. Okay. Omega n is known or not? Okay. Before that, let me say. So you know omega n. What is that omega n? Omega n is undamped natural frequency. That is k by m. This omega n is also known. So you also know what is called as Cc, critical damping coefficient. That also is known. 2m omega n. So you also know what is called as zeta. What is zeta? Zeta is equal to c divided by cc. So these are also known. Okay, they are not the parameters of the system, but once you know the parameters of the system, probably you can call this K, M, C. You can call it as parameters of the system. Therefore, I know that zeta is also known, C equal to CC. All these things are known. Please remember, these are all known. These terms I am going to use it later on in my analysis. So I shall go back for a while now. For a while. Okay. So what is the order of the differential equation? This is second order differential equation. Definitely this also shall have two constants. This also shall have two constants. Okay. So please remember here mx double dot plus cx dot plus kx equal to f naught sine of omega t. I shall take back to you to your differential equations classes. Okay. I am not going to discuss anything. Okay. So what you might have studied, if you have attended, definitely you have studied it. If you have missed it, probably you can spend some time. Okay, and whatever is required for my study, I shall pick it. Okay, for this kind of equation, something here, second order differential equation, and right hand side is not 0, and right hand side is also something which is a function of time, say the same thing here, variable. Okay, in that case, we say that solution of this general solution of this differential equation is in two parts. We see that what is x? X is the general solution, x of t has two parts in the what is called as xc of t, that is called as complementary part of the solution, and the other part of the solution is what is called as a particular integral. Okay, I don't know whether something is igniting that you had heard this kind of word. Definitely the same kind of words you will hear there you might have heard there also. So the solution of this has two parts. One is called as the complementary part, xc of t. The other one is called as the particular integral, xp of t. Okay, then what is xc of t? Xc of t is also known as complementary part. Complementary part is the solution of what? Again a differential equation, which is mx double dot plus cx dot plus kx is equal to 0. If you make the right hand side 0, then you have the solution, and that solution is nothing but the complementary part. The complementary part of the solution is given by the solution of this mx double dot. Okay, so does it make any sense for you now looking at this equation? This is the same thing what you have studied under what is called as damped free vibrations. Okay, what is the solution of this? The solution of this is nothing but xc. The solution of this equation is xc. So then now I can write xc of t is equal to. So xc of t, the solution of this depends upon three factors. Whether the system is overdamped, then you have something. If the system is critically damped, then you have something. If the system is underdamped, then you have something. So therefore, this xc of t depends upon what? What is that? Number one, xc of t may be 1. What is that? E raised to minus zeta into omega n into t into bracket c1 e raised to minus root of zeta square minus 1 into omega n into t plus c2 into e raised to plus root of zeta square minus 1 into omega n into t. This is what is called as the overdamped system. If what? If zeta is greater than 1. Okay, now you have to find out, as I said, zeta is known. Zeta is more. If zeta is more than 1, then xc is this. Okay? Or number 2. What is that? If zeta is equal to 1, then what is that? C1 plus C2 into T into bracket e raised to minus omega n into T. Please remember what is left hand side. Xc of T is equal to this. This is what is the meaning of that. I am writing one or. So if one is not correct, then applicable. What do you mean by applicable? You have to check what is zeta value. If zeta is greater than 1, 1 is applicable. If zeta is, if this is true, if zeta is equal to 1, if zeta is equal to 1. Okay, so or. What is the third one? The third possibility, if zeta is less than 1. If zeta is less than 1, so I had three different forms. One of them I am writing, say C e raised to minus zeta omega n into T into bracket, bracket is not required, sine of omega dn into T plus 5. This is what I have. Okay, any one of this. This is when if zeta is less than 1. So zeta equal to 0, that is nothing but undamped system. Okay, in that case it becomes, that also it is okay. Zeta is equal to 0 is also for this case only. Zeta is less than 1. So that means I know what is the value of xc. Xc part I know. Please either this or this or this. Okay, one thing you have to observe now, I need your very careful observation. Whether zeta is more than 1 or zeta is equal to 1, zeta is less than 1. Okay. Anyway, we had spent some time, some detailed study on this, zeta less than 1. So what happens? The amplitude of vibrations, in this case, only here you have vibrations. Here you don't have vibrations, here also you don't have vibrations. Here you have vibrations. And what happens to the vibrations, amplitude of vibrations? The amplitude of vibration is continuously decreasing, and after some time, the amplitude becomes so small that xc becomes 0. Or in other words, you will not have vibrations after some time, because it is a damped system. The free vibrations, because of this xc is nothing but the free vibration component of the solution. Okay, so this solution, these vibrations become 0 after some time. The same thing holds good here also, because of e raised to minus omega n into t. As t increases, this value becomes smaller and smaller and smaller. So practically after, say if I take after 10, 15 seconds, 20 seconds, this becomes so small value that the whole thing becomes very, very small. And this is true with this also, because here you have e raised to minus zeta. Zeta is also large, more than 1. Omega n is large, and as t increases, this becomes smaller and smaller. And when you multiply this here also, all these values become smaller and smaller. And as t increases, okay, then xc becomes 0. Very, very, very important. Okay, so please observe. What is that observation? So I shall run this space now. I don't need this diagram. If required, I can draw it very easily. So I have to make certain observations. What is that? So xc diminishes or becomes very small. Very small, practically 0. Theoretically, I cannot say that it's 0. It will be 0.00000 something, some value. Okay, something like that. Practically 0. Okay, after some time, that is after few seconds. Okay, I shall go back here. What is that? So x is equal to xc plus exp. Of course, x of t, xc of t t, xp of t, etc. All that is there. Okay, so then I have an observation. So if xc and xp are not zero, that is very beginning. So that is very close to t equal to 0. So you have t equal to 0, you start the system. Then maybe after 0.1 second or 0.01 seconds, okay, 0.2 seconds, something very close time. Initially, this is what I mean. If xc and xp are not 0, that is at very beginning, at very beginning, at very beginning. Okay, then the system is said to be, then the system, we say that the system is in what is called as transient state. We say that we have a transient state. When xc and xp, both of them are not 0, xp will never be 0. xp will never be 0. It is only xc. If xc is not 0, if xc and xp are not 0, okay, in that case, then the system is, that is, I can say only this. If xc is not 0, if xc is not 0, then the system is said to be in a transient state. Okay, if xc is 0, then what? Then x is equal to, or x of t is equal to xp of t, and just wait. This state, this is known as steady state. This is known as steady state. This is known as steady state. We are interested in studying what is called as steady state solution of this equation. We want to know what is the steady state solution of this equation. So mx double dot plus cx dot plus kx equal to f naught sine of omega t. This solution, I want to know what is the solution. The actual solution is the sum of these two. But in very soon, this becomes 0. In that case, x of t is equal to xp of t. That state is called as steady state. The system has reached a steady state. So, for that steady state, what is the solution? How the vibrations are taking place? And that part of study is called as steady state vibration. Okay? So, now, I would like to continue the steady state solution of this thing. The next subtitle I shall slightly change it now, the continuation of this itself. And what is that? So I want to know what is the steady state solution. Steady state solution. So this is what we want to get it. And I shall write down for my reference. I am going to rub this and make this clean. And I shall write down what is the equation. What is the equation we want to solve it? Mx double dot plus cx dot plus kx is equal to f naught sine of omega t. This is what I want to know. So I want to know what is x of t. X of t is equal to xp of t. Okay, so now I want to make some logic and assume certain logically. I shall assume a value for what is the expression for xp of t. And then I substitute that back in this thing, and then I shall solve it. Okay, the solution also is a typically different method. We go for what is called as graphical solution. We go for graphical solution, but you don't have to use any of the drawing instruments, nothing, that is not required. We are going to have a very simple diagram, and our making use of our trigonometry or graphical relationships, Pythagoras theorem, etc. I can straight away write down what is the amplitude, phase difference, etc. whatever the unknown things. Okay. So now So the best thing is, what is xp of t? So what should I assume? Okay, so now I shall go back to the diagram whatever I had. So this is the system. What is xp? xp is basically the displacement of the mass. The displacement of the mass. Okay. So one thing, first thing, okay, as I am going to apply a harmonic force, okay, that will make this mass to move up and down. It is a harmonic force of frequency omega, and therefore when I apply force, then only it will start moving, and this also will be moving at the same frequency. Okay, the first thing what I assume is, so logical is frequency of, okay, so xp is also harmonic. This is the first logic I would like to apply. I am applying a force which is sometimes this way, sometimes this way. That is why the displacement is sometimes this way, sometimes this way. So therefore, the displacement is also harmonic. And what is the second logic I would like to apply? xp also has same frequency as excitation. So that means the frequency of xp is also omega only. So I have applied a force, what is called as f naught sine of omega t. This is what I mean by frequency of the external excitation. External excitation frequency and xp frequency, both of them are one and the same. Okay, now the third possibility is, what may be the phase difference? The phase difference between xp and this force. Which do you think they are in the same phase difference? Maybe possible. Do you think xp is ahead of this force? It is impossible. First you apply force, then it will take some response, some time it may take, then only the motion will start. For example, if there is a friction, so you apply some force, because of friction, the mass is not going to move immediately. If there is no resistance, then immediately it will start. But in any case, the force is coming, that is why the mass will start moving its motion. That will never happen. That means xp is never ahead of this force. xp is never ahead. At the most, what may happen? The force, the moment it is applied, immediately, without much wastage of time, immediately it will start motion. But it is logical that in general we have some resistance, we apply some force, it will take some time in the sense it is fraction of a second, it is not minutes together. Okay, it will take some time and then the motion will start. So what is the meaning? So you have some phase difference between xp and the excitation, and xp lags. Okay, xp has a negative phase difference. xp will follow f naught, follow external excitation. xp shall follow external excitation. Okay, so these are very important. Making use of all these, we shall assume a force. Okay,